Yeah, now it's quite visible, quite visible.
Okay, okay, okay. Full screen mode. Okay. So thank you very much, sir, for a nice introduction. And actually, I'm not like that. I just we are also learning, and everybody is learning. And you are more senior than me. Thank you. So, I welcome everyone for this session on advanced power converter control for solar and wind application. So most of the time in India, we just imitate some kind of the power renewable energy we see in other country, and we come back and put a different solar plant, everything. But sustainability actually day by day reducing in this particular renewable energy. Although we are integrating more and more into the grid, but it is different place require different kind of investigation, and that is why India is unique, especially the manpower, especially the skill of the people, especially the skill of the investor, and especially the mass mass education is one of the biggest challenge in India. So in other countries, they are well known actually what to do, what not to do. For example, in Gujarat, long back I was visiting to one of the wind farm near Rajkot. Actually, I visited there. I have seen because it is on a small this field. So there are in the night time there are many buffaloes. They come and they stuck to this wind turbine. They sleep there. Something happened, and that is how the wind turbine sometimes vibrate. And due to centrifugal force problem, there are many things happen. So and sometimes you connect to a low voltage grid from the wind turbine, and when you integrate, sometimes low voltage grid is hooked by the local people, where it creates another kind of problem. So there are many problems actually, and recently we developed a 1 megawatt solar plant for the Port Blair Air Force Station. And the challenge was tremendous because especially in Port Blair, there are a lot of sand particles strike on the panel, which destroy actually in due course of time. Although outside you will see the panels are very good, but inside there is some kind of breakage in the microelectronic circuitry. So that way, although we are seeing that if the panel is very good, but efficiency comes down like that. And second one is the structure, especially in India, especially in Port Blair, and you come to Odisha also. Most of the time there is some kind of cyclone, and this cyclone can damage actually. They can uproot a big solar plant also. So in India, everywhere there are different kind of challenges, and you cannot map. In Western country, they can map. Oh, I have 5 kilowatt. I have experience. I can put 500 kilowatt. That is just mapping actually. But in India, you cannot map exactly because every geography in India are differently situated, and people also they differently understood the thing. For example, long back near Raigad, there was a Naxalite area. In that area, they wanted to put IoT-based smart system, and in that system, we tried to establish a IoT-based the detection system. If any human being or anything moves in that area, we can recognize it. So when we put the solar panel, and it was running for some time, but after 1 week, all the tribals they came and they thought that it is some kind of flower, and they thrown the stone and it is damaged. So this is the need some kind of introspection and properly giving the education to the people in general are the biggest challenge. So today I will discuss few projects also, what are the challenges and how to we taken care of that one. And that way today we will discuss some advanced power converter control. Generally we know the control, okay, everybody knows power converters and everybody know what is the control, but what is new we will see today. So for example, I will tell a beautiful story. There was a very poor woman, and her name was Revati, and she was very poor. She lost her husband, and she was working on others' home and getting some money and teaching to his son. Okay, and she thought that my son should become a barrister. In olden days, barristers are a very big post, like a so they have to go to England and study the barrister. So she thought that let me bring a good tutor who can teach my son very nicely. And after that, this lady actually becomes very happy, and he was that boy reached 8th class, and the that tutor who was there, he started teaching. Let's ABC be a triangle. So this lady became very angry, and she told, my son in the other room, she was in the other room, she thought that my son has already studied this ABCD when he was in class 1, and now this teacher also teaching the same thing. She became so angry and came inside and told, you are not a teacher, proper teacher, you get out from this place, because my son already read this thing. And she was not hearing anything from the teacher. At last she removed the teacher from the home. So this is our condition. We do not properly plan it, and we try to receive the things quickly, as we see from the other country or somewhere. So today we will discuss, there are many design projects which we carried out in the different places in the Bihar and in worldwide, in USA also, in India also. And then I will speak about the grid connected current source inverter fed PV system. I think most of you knows that voltage source converter fed induction, the fed grid system or grid integrated VSI connected to the grid system. I think most of us we know, and today also it is very popular. But CSI, I think very hardly we know about it. And there is a concurrent design methodology for grid current feedback. So generally, you know, like you have a two kid. So both the kid, one kid is doing very good study, other kid is doing very good music. Both are in the both directions actually. So you, by staying both of them together, he will also get some benefit, and both of them, they will exchange some of the idea. And that is called the coupling effect. Like we have you say that it is a coupling, means because of his music, he is influenced a little bit about for singing or some music. And because of his studious activity, he is also interested a little bit in this study. So like that, this current control and grid connected system also exactly like that actually. So they are coupled network. So we need to proper control. So that is why grid active damping we have, and we will discuss about voltage source converter fed PV system with LCL filter. And then we will show many the experimental setup. Then we will discuss a little bit about intricacies of double fed induction generator based wind energy. So this is a modeling and control design of a grid connected current source inverter. You see here, this is a current source inverter. How you know? Because in the input there is a PV and then there is a large inductor connected, which behaves like a constant current source. Large inductor behaves like a constant current source, like a large capacitor behaves like a constant voltage source, like a battery is a constant voltage source. So you put a capacitor that is also a constant, the constant current. And you see for current source inverter, you need to have a unidirectional current. So bidirectional current is not needed. Why? Because in the current voltage source inverter, you can control the voltage, but you cannot control the current. Current can be any direction. That's why you require bidirectional switch. And in the current source inverter, you can control the current, but you cannot control the voltage. So for controlling current, what we have a unidirectional switch. You can see after this IGBT, there is a diode connected in the series, which makes the complete device as a unidirectional device. That means the current will flow in one direction. And that is what, but the voltage can be reversed, but current cannot be reversed in a current source inverter. And then we have a LC filter, which filter out the switching ripple, as well as it will give you the pure sinusoidal output connecting to the grid, which is EA, EB, EC. So there are 6 switches, and this is the current source, and they are connected through the filter and to the grid. And sometime you will find after the filter there is also interfacing transformers also. And after the transformer they connect to the grid. Now the control scheme is very important. When you need to design the control. The first thing is, you see here, this is a PV system, and this PV system, what you have here, this is a PV system, and we want MPPT. First thing is, you need maximum power always. So MPPT algorithm, you can use this VPV and IDC, both you measure by current and voltage source. And then MPPT algorithm, when VDC reference and measure actual VDC, and then this PI controller, and from there you will get the change in the voltage, okay? And accordingly, you have measured by using 3-phase PLL, phase lock loop. I think most of you must be knowing what is phase lock loop. Phase lock loop is to fix both the frequency as well as phase of the system, lock according to the input. So sometimes we also use a small transformer just to get the phase of that system. So this phase lock loop means it will fix your input and output frequency. They both have same frequency. F1 is equal to F2. And another one is constant. Also, second one is that this phase lock loop will ensure, okay, that if there is a constant phase shift, it will maintain at the output also. So that means mainly we use this one like a full synchronization. So you get the information of angle at which you want to inject the voltage. That is the most important thing, that you want at which angle you want to inject the voltage. Exactly you get from the information of this phase. And after getting this, then you have modulation block, and you have a ABC to DQ, I think, to 3-phase to 2-phase, 2-phase to 3-phase. transformation, we already know all these things. And from there, you can get the switching inverter. Now, you see, this is a mathematical modeling, and I am not going to discuss detail because this mathematics you can design. The most important is the concept, it's very important. Then the mathematics, okay? Mathematics, everybody knows it. So now you see here, the modulation index here. I have this modulation index delta 1 minus delta 4 is your modulation index. This delta 1 means upper switch when turned on delta 1 is 1 and lower switch turned on or delta 4 is turned on, it is minus 1. And that way you get 3 balanced the modulation index so that your output current will be balanced one. If your input is or modulation index is not balanced or the reference is not balanced, and then output you will not have balanced output. So these references I will discuss in detail when we are coming in the current control. Now we are not going to discuss, and the modulation index also I can tell you it is between 1 actually. Why? Because actually we are not cannot operate at 1 also. We go up to 0.866 modulation index as a linear range. Above that, it is like a saturated range. What is the saturation and what is the linear range? Linear range means input output mapping. Y is mx is your linear range. Okay. So y is mx plus f of x something, f of x, y, t or like that. So it will become a simple kind of saturated or non-linear system. So this symmetrical, the grid voltage also you will get. And if you see here, you can find out for the continuous conduction mode, because there are 2 kind of conduction mode. One is continuous conduction mode. Another one is a discontinuous conduction. In the continuous conduction mode, most important thing is the continuous current. And the discontinuous current conduction mode, there may be some part of the cycle where the current is 0. So that is called. Anyway, this plant model we can design like this by using KVL equation, simple Kirchhoff's voltage law. And this is the equation, VPV is this one. And this is the complete loop equation. Now, this plant model we can derive by using this one as the line voltage plus VDC, okay, load voltage and plus this. Then you just mathematically manipulate this one and you will find what is the MQ, MD is Q-axis modulation index and D-axis modulation index. And then we can draw the phase and phase margin and gain margin of the plot. From there you can ensure that the system is stable. The closed loop system is stable, which is very, very important. Okay, when if the system is stable, then you can use it. So there are some constraint in current source inverter. So there are 6 switches we have seen already. And in 6 switches, if you have a voltage source inverter, we know that. The voltage source inverter, we have seen that voltage source inverter has 6 switches, and you have 180-degree conduction mode and 120-degree conduction mode. So 120-degree conduction mode, 2 switches are on, whereas 180-degree conduction mode, 3 switches are on. So similarly here, you have 6 number of switches, and these 6 switches, they require continuous conduction because it is a current source. That means at least 1 switch from the top, 1 switch from the bottom, they should always on. If there is no on, if there is 1 switch from top and 1 switch from bottom is not on, there will be no constant current flow, then it may damage one of the switches actually. So that is why we all must know that there must be a continuous conduction path in one switch in the top and one switch in the bottom. And then this may also sometimes damage the switches, okay, forcing path to appear. For example, if you see, I have used, for example, a thyristor. Thyristor is a 4-layer device, and there are 3 junctions, J1, J2, J3. One is PN junction and NP junction, then again PN junction. In forward bias, 2 junctions are forward bias, 1 junction will be reverse bias. And in the reverse bias, 2 junctions will be reverse bias, 1 junction will be forward bias. For example, so when there is a leakage current, for it is a forward bias, and suddenly one switch is off, so only one switch and the top switch are open. So what we will do? So there will be, as soon as it is forward bias, there is a leakage current in the junction J2. So that leakage current due to the inrush current, like the inductor, it impinges the current into the channel which is formed between N and P. That channel there will be large amount of current which will come through that channel, and there will be hot spot, and that switch will damage. And that is how the switches are damaging when you don't have 2 paths, one switch from the top and the switches from the bottom. Another one, there are more than 2 switches on. If 2 switches from the top, or 2 switches, or 1 switch from the down, or 1 switch from the top and 2 switches from the down, if it is on, then what will happen? It will create undesirable and uncharacteristic harmonic, where you cannot design a filter for that. So uncharacteristic means you cannot define. Like for example, we have a square wave. What are the harmonic? We get first, we have fundamental, then third, then fifth, then say all odd harmonic. When you have a quasi-square wave, so quasi-square wave, you will have absent of third plus multiple of 3 harmonic, but you will have 5th, 7th, like that it will come. So if it will come 1.5, okay, that harmonic will, fractional harmonic, you cannot define those things. So that is why it is very important. So based on this discussion here, so we found out there are 6 active switches, I1 to I6, which is, you can see that these are the states, and 3 null switches, I7, I8, and I9. And these switches, the null switches always give the output current 0. And if you see, each switch, for example, S1 is conduct for 60 degree at a time. So S1 conduct for 60 degree, you see, S3 conduct for 60 degree, S5 conduct for 60 degree, S1 conduct for 60 degree. So like this, it is repeated. Okay. So this way we are control this one, and we have this is the modulation index, and then we have the getting signal generator. Then we are prepared. So if we see here, you can see the reference current. This is the IDC reference. Okay, this is our reference current, and the current IDC. You can see that actual current is black thick line. Okay, this actual current. This actual current, what is you see average over a cycle, you will see that average current is IDC reference. So that way you can see that it is actually tracking the reference current. And when you are feeding to the utility or grid, then you can see that the both current is smaller one, grid current and voltage, they maintains unity power factor. So unity power factor means what is this? This is called the utility friendly, okay, device. Okay, utility friendly means that you are operating at maximum power. For example, in our circuit theory, we all know What is the maximum power? When input impedance is equal to output impedance, then you can achieve the maximum power. Okay, that is the maximum power transfer theorem. So, but here you can see here, so when input and output, okay, they both are, if they have same impedance resistance, then you get maximum power. Similarly, our power factor is VI into cos phi. So V into I into cos phi, but in power electronics, it is not VI cos phi, it is a displacement factor and distortion factor. When the displacement factor is 1, then complete unit is like a 1 only. So you can see that this is the nothing but the maximum power transfer to the grid. Okay, that is why the unity power factor means also it doesn't draw any reactive. So, so sorry, just I was hearing some sound. So okay, this is how you can transfer maximum power, and you can see that when it is operating at unity power factor, you doesn't require any reactive power there. Why? Because whenever there is a reactive power, what is reactive power? I told that reactive power is the only the carrier power. For example, you have a small kid, newborn baby. You cannot take that newborn baby in your hand. Although, what you will do, you will put some cloth and then carry, or some cotton, you carry that baby from one place to another place. So this cotton is not important. Important is your baby. So that baby is nothing but your active power. And the cotton which carries this baby are called the reactive power. And that is not important. Cottons are not important. But which is important? The baby is important. But can you take a baby without a cotton? You cannot take. That is why inherently the lines have the reactive power. And that is, but here in this converter, you operate at unit power factor. So reactive power is nearly 0, because VI into cos phi, where cos phi is equal to 1 and sin phi is equal to 0. So that is how reactive power is always 0 in a utility friendly converter. So then you see here, this is the modulation index. And what this modulation index says here, you see initially there are harmonic switching, or the black color, there are a lot of ripple, okay? And it is a very important criteria actually. Most of the time when we do experiment also, we actually remove all these things. We say that, no, this is not important for me. No, you will see that this is called the chattering. Chattering means these are the high frequency or harmonic switching. Okay. So what is this chattering takes place? Why it takes place? There are many causes actually. There may be noise or high frequency noise due to the switching of the converter, which is propagated to your control circuit. Second one, it may be due to line strain inductances, that your resonant, there may be a resonant effect with your, that may also create more electromagnetic interferences. Or it is due to the harmonic switching, means at the same time they try to stabilize the system very quickly. So these are the harmonic switchings, okay? So initially you get this harmonic switching, and then as steady state come, you can see that it is operating within modulation index 1. So this harmonic switching has a big effect actually. This, if you even just you study these harmonic switches, you will it has a lot of potential. Then you see this is DC voltage, okay, voltage DC voltage, and like this, if you have a voltage source inverter, you will see that capacitor current will be have like this wave shape, where now you can see that voltage, okay, VDC. Now, this is the three-phase current source inverter output. You can see here, they all are the 120-degree phase apart from each other, okay. So this all are, they are 120-degree phase apart, and this A phase is B phase is 120-degree phase apart from, and the C phase is 120-degree, like that. This is the complete balanced output. And when you pass through this filter circuit, you can see that this is actually this lower one is our current and upper one is our voltage. So that way you can see that our this grid current and both are at a unit power factor, and this way you can now you see this is our injected or the current harmonic, which is less than 5% THD, and then voltage across the output filter inductor, okay. So this is the output filter inductor, which is and the capacitor the voltage, okay, you can see here they both are actually, this is these are the, you can see that which is absorbed here in the inductor. This you can see that the area represents the small storage of the energy, okay. Then you see the FFT of the filter capacitor and voltage here also. You can see that this is the capacitor current, the one, you can see that they all are symmetrical. And to test the PLL, phase lock loop, that we deviated our frequency from 50 hertz to 48 hertz. So you can see that the PLL is tracking to the input voltage just within one cycle, 1.5 cycle. So within 1.5 cycle, this synchronizes with your input waveform. Okay, this is what your PLL shows here. Okay, filter. And this is the hardware module where we use the hardware setup, and you have a input, then we have a current and voltage sensor, then we have a inverter and feeding through this inductor to the. So this is, we used the semicron IGBT, and these are the hardware where we did result. We take result to hardware. You can see that current error, and you can see that there is a current is tracking according to the reference value of the current. Okay, so these two are very important things. So most of the time, you see, in the current source inverter is implemented, and this current source inverter actually, they are very good performance as compared to voltage source inverter, and current source inverter is very robust. How it is robust? Like in JK paper mill, I was working initially, so I saw that current source inverter fed synchronous motor drive. So during the pulping time or the paper when you are doing, so the motor should be very stable actually. If motor will vibrate a little bit, the quality of papers will go down. So to keep that one, what we did, so the people use the current source inverter, because current source inverter, even if there is small voltage fluctuation in your line, current source is a constant current source feeding to your line, which will not affect. Okay, that is what the current source inverter has a lot of advantages. Okay. So then we will see a concurrent design methodology for grid current feedback active damping LCL based grid type voltage source converter. So this work I did with along with Professor Ojo in Tennessee Technological University long back. So we designed this one. So this is what the proper description of the system. So if you see here, this is a controller. Okay, you have a voltage source inverter connected to LCL filter. Okay, L and C and L filter connected to the grid. So from there here, how you can design? Okay, one is I told you the current controller. Current controller, what you need? You need information of theta, because without theta, okay, you cannot synchronize any gate, any gate. So when we get this theta PLL and you find out the I D axis and Q axis current, and we have a current controller and then PWM it switch on. But when you have a current controller, what is the problem? Problem is with the resonance. So in voltage source inverter, there are three kind of frequency component. One is your first switch frequency component is your sampling frequency. Second one, resonant frequency. Third one, supply frequency. So when three frequencies come into together, and what is the relationship between them is a big research area. Okay. So what is the relationship between sampling frequency and the switching frequency, and then resonant frequency. So how to do that? And this is the biggest challenge. Okay. Now, after this, then what happened? We have both current controller. When you have a current controller, these three frequencies will affect to the system. If there is a, you may say that there is that resonant. Resonant means what you mean? Resonant means the circuit will behave like a low resistive path. Okay. So when you have a LCL filter and the circuit is you want to filter out at resonant, so what you do? You need to choose proper frequencies for the resonance, because the resonance is depend on the plant parameters, for example, L and C. Okay. And the switching frequency is depend on your power converter. If it is 20 kilohertz, for example, IGBT. IGBT you get, it can switch on up to 20 kilohertz. So according to, you have to choose your switching frequency. And sampling frequency with respect to your particular engine. For example, you have a small computer and that sampling frequency is controlled by that computer, computer switching, computer. So that is why these three are distinct frequency, and how these are interactive, there is a long story actually in this one. Okay, so that is what, to control this resonant and to get high performance, we have added another path with parallel to the current control, that is called active damper. So in the damper circuit, I think all of you must be knowing, in the damping winding in a synchronous motor, there are damping bindings. So what that damping binding does, it damps out the oscillation. So how it damps out the oscillation? For a layman, how you will teach that? How it damps out? For example, you throw a big stone in a river, in the pond. So as soon as you throw a stone, the river will create a wave motion. Okay, the water there will be a waves. And how to stop that wave? Even if you go and put your hand, the wave will not stop. Again, it will move like that. So when the wave will stop, when you put another stone, and in the distance, which will produce opposite waves, so they both will cancel out. Similarly, in the dynamic system, when you have a dynamic in the voltage or dynamic in the change, or there is a dynamic, you need to produce another dynamic which can compensate that. And that is called this parallel active damper. That even current controller has no capability to decouple the thing, whereas the active damper helps us to decouple that thing. And that is what the closed loop PLL, then DQ ABC to DQ transformation, then current control, then active damper, then this PWM, then switching. Okay. So what is the important here? The use of LCL filter, and their advantage and limitation of this one. And the issue of LCL resonance is biggest in our design aspect. And then the effect of system parameter variation and resonance frequency. And passive and damping acting, okay, passive, generally passive damping we sometimes give, okay, where are low cost, that's why it is passive damping is also important. And then current controller design by using optimization method and approximate calculation of the controller gain, neglect active damper of the high pass filter, and poor dynamic low resonant frequency of the LCL filter. So what is the motivation? Motivation is novel technique to simultaneously design an active damper and a current control, both. For example, you want to go and you are sitting on a rail, and one side you are sitting, and the other rail your friend is sitting. So when you are moving, you are seeing that both of you doing simultaneously activities. For example, what is the advantage of simultaneous? For example, there was a student in IIT Delhi. He was a research scholar. So that student told me, sir, I have, I generally, I asked, you have so many papers, so how you do it generally like that? So he told, sir, what I do, I generally prepare 5 or 6 papers at a time. And when you put at a time 5, 6, so if you check the similarity index, it will not come. Because 5 papers, there may be same result, but they are parallelly you put, so people, some papers, they will be accepted. So similarly, this simultaneously current control and active damper, they both are designed here, and satisfactory performance independent of the ratio of the resonant frequency of the LCL filter, rather the sampling frequency of the control. So I told you there are 3 kind of frequency. One is your switching frequency, one is your sampling frequency, and another one is your sampling and switching frequency and resonant frequency. So now from the 3 phase you can transform, we can transform it into 2 phase, okay, ABC to alpha beta to DQ, okay. So this transformation matrix, okay, by coordinate transformation, and you can design the control. And when this is designed, then you can see that the active damper is nothing but like a second order, okay, low pass filter. And you see that there is a distinction of the state space representation. These are the mathematics, so we skip this part. And if you want more to know, you can write me. I will give in detail. Okay, this is how you can do the modeling. Okay, so then we can see that there are this state space representation. You can represent everything, all these parameters in state space, and then here the design starts actually. First thing, the first generally what we do, we design the current controller. Okay. First we design the current controller. Then we again design the LCL filter. So by designing that way, what we are losing is that we lose many things. First thing is that when you design the current controller, so as soon as you design the current controller also depend on many parameters. For example, hysteresis band, it design also it depend on the resistances in the network. So all these things come into picture during current control, and then LCL resonance. So when you simultaneously design both of them, then the resonance effect will not be there. So resonance will not be there. That is why the first we must design, simultaneously we must design. You see, this is the relationship between the sampling frequency and the maximum crossover frequency. So what do you mean by bandwidth? Sometimes you say that we need to give a large bandwidth. Means what is that? The bandwidth is that, for example, in your house, you are making a door. And door you can make around 2 feet or 3 feet. And if there are little fat person, he will come, he cannot enter the home. So when you create around 5 feet, and he can easily come. That means what you do, you just increase the bandwidth of this door. That's all. The width of the door, okay, at which you want. So exactly similarly, this bandwidth or higher bandwidth means that is dynamics are allowed to flow. For example, the dynamic can jump to any height. So that is how the bandwidth, higher bandwidth. But higher bandwidth require a lot of cost. So that is why the bandwidth is always controlled. Okay, and because once, for example, your child, you told your child, you go and bring one pen and pencil from the market. He can go and bring. But you cannot tell your child, go and purchase a car and come to you. So there the bandwidth is not given. That bandwidth only Papa has, where he can go and purchase anything as he likes. But a child cannot purchase. And that is called the bandwidth, that how much you allow the dynamic to do or to flow, okay, dynamic to participate in this. So then there are many mathematical equations for the different controller, everything. So if anybody has any questions also, we can discuss. If you have any question, you can just stop me, and I will be happy to answer. I try to answer the questions. Okay, if you have anything like that, or you can put in your chat box also, and this way we can you can also we can discuss this. So anyway, then these are the controllers. Okay, different control K, Ki, then. And these are the different parameters. So what this is the LCL based system parameter. You can see that DC bus is 380 and 120 volt then frequency. And this is your LCL filter, okay, parameter. So LS, if you see this filter parameter, okay. So L is 8.4 millihenry and LR is 2.5 millihenry. So if you take, you can see that two band, one is 6 dB and 3 dB, okay? So there are three these parameters. Now, so what do we do actually here? What do you mean by root locus? We know the root locus is that where T to find out the stability, okay? If the poles are situated on the left hand side of S plate, it is stable. Does every network can come to the stability? No, every network not. Actually, we linearize the switching. Switching system are always, they behave like a nonlinear system. And when we have this switching system, and you apply this in the root locus, so you design the linear, bring to linearization, then you use this one, okay? But if you see a nonlinear system, so what is that? That is called phase trajectory or phase plane analysis. What is phase plane analysis? For example, you are in a space, for example, your home is in the Agartala, in NIT Agartala. That is your origin, okay? You may say that that is the origin. And what is that? If you start from maybe Chennai, somebody start from Bombay, or you start any point, if you reach to your home by any path, okay, there may be some path through Nagpur, some path maybe through Bhubaneswar, some path maybe through Delhi, okay, if you reach somehow or other to your house, then you are a stabilizer, okay, that is what. So similarly, in the nonlinear system, you start from any point in the space, as t tends to infinity, you reach to the origin. That is the most important thing, actually. So similarly, here also, in this one, what we did, we vary the gain, okay, and the locus may start at any point in the space, but it comes to the origin. Similarly, like you come to your home, is the one. And then, if we cannot reach to the origin, so what we do, we have an extended space or extended small radius, which is maybe epsilon, very small. And if the system trajectory comes and stays in that region of attraction, okay, that is called the region of attraction. If they reach, and it is called asymptotically stable. And that is what is treated down here. Actually, we changed the parameter of the controller, and the controller, they behave as they started, and at last, at t is equal to infinity, they reach to the neighborhood of the origin or at the origin. Okay. That is how these three schemes are given for different value of k and different values of the gain constants. And you can see that here there is a border plot of 6 dB and 3 dB. You can see there is a regional peak in the 3 dB system, where when you increase the bandwidth, you can see that there is no regional peak. And you see here, this is the simulation result of the grid current response, and for the system with 45 phase margin and 6 dB gain margin, and this one is for 45 degree phase margin and 3 dB. You can see that the when you have a large gain margin, you can see that the system stabilizes very quickly. When you have a less gain margin, you can see that system oscillates for some time. So this is what, for example, in your home, you have taken food, full stomach, and you can run for 10 kilometers. After that, you will feel little hungry. And you have taken just little food, and you want to go 10 kilometers. It is not possible. So that is what here it says, that the large bandwidth stabilizes quickly, and the smaller bandwidth or the smaller gain margin, they take more time. And that is what here is said. You can see that D axis and Q component, they both are decoupled. You see, when you are there is a change in the Q axis component, there is no effect on the D axis. And this is called the decoupling method. How you can decouple this system. And you can see here, when you have lower gain margin, you have sustained ripple or current ripple is observed in the waveform, whereas if you have a large or 60 dB gain margin, you have lower the current ripple. So this complete unit is investigated and implemented here with our system, and you can see here this at 3 dB. These are the experimental results. At 3 dB, there are actually switching, and when you have a 6 dB, you can see that smoothly it is actually changing. But what do you mean by this 3 dB and 6 dB? Sometimes this is like you have a staircase to go to one layer to other layer. Okay, so you have 1, 2, 3, 4. Let's say 4 stairs are there to reach to that point. And sometime you may also jump from lowest to that 4th step also, just by jumping like that. You can do that. So when you jump like this, and you can go by staircase, when you go by staircase, that is the, when you go step by step and reach there, there is a sluggish response. But when you jump there, it is very quick response. But most important thing is that at that quick response, there may be destabilization. Because as soon as you jump, you may fall down. If you are stable, you can be there, or else you can fall down. So like that, when you increase or decrease this bandwidth, the same effect is observed. When you decrease, the response is a little sluggish. When you increase, the response is very fast, but there may be also destabilization also. So this way you can also see these experimental results that at 3 dB they are actually a lot of ripple and takes a lot of time. And the conclusion is that this we designed the decomposition methodology we use for current controller, concurrent design of the current controller. And there also you can define gain margin and phase margin. Everywhere you see, you design the gain margin and phase margin. Okay, you do yourself the gain margin and phase margin. You design that one, then you get some gain margin and phase. Here you just put gain margin and phase margin, then it will be designed, okay, according to your requirement. And this complete system, when you have a concurrent design, you will see that a complete system is independent of resonance frequency. You have not seen any part of this derivation. There is an effect of resonance frequency. Okay, that is what independent. And no expertise parameter tuning are not required. Okay, and then the simulation result and experimental result, they show the validity and effectiveness of this system. So there are many references. So if you have any question or comment, I can answer one or two. Or if there is no such thing, then we can go to other part. Okay, if we don't have, then we can go ahead. Okay. Right. So then we will, most important thing is that we will now design grid connected, okay, TV system, low voltage, ride through capability. And this is a very important thing today. Although we put many grid connected system, but low voltage ride through is one of the great challenges today, because generally in our power system, conventional power system, the generator are connected with a big flywheel, and flywheel stores the energy. Then whenever there is a dynamic or quickly you require some energy, so the flywheel support, then by using automatic generation control, AGC control, so you again come to the steady state of that is angle to equal area criteria. There are many angle stability, everything they come. So this LVRT, low voltage ride through, is also is a great challenge in case of a solar plant, because solar doesn't have like that stored energy unless there is associated with a battery. So if you see today in the great code of India and the world, the people they want that our plant should never be disconnected from the grid. And when there is a large voltage fall, for example, there is short circuit or something, so that time you see that your voltage will come down. And this voltage, during that period also, because voltage will come down and you have a constant power type of load, so your current will be very high. So it will damage the entire converter system. So during that period, how you will be connected? And that is also one of the challenges today. And then we have a simple a boost converter, and we design with the load, and this is extended for our this is a MPPT or VI PV curve of that one with, and then we have a hardware. You can see that this is DC converter. Then you can see there are phase lock loop, okay, synchronization. How to synchronize this system? So you can see that this is the PLL. This is orthogonal signal generator PLL. Okay, and then this is there are different kind of PLL, and I am just showing you the structure of PLL, and you can go through this literature. There are many papers available also. So then there are second class of PLL is second order generalized integrator PLL, then cascaded second order generalized PLL, and then SOGI PLL. Okay, then we have a modified SOGI PLL, and you can see that here, although we have discussed all these things, but we have not. This you can see that we have discussed all this, including design. Okay. So design guidelines, okay. So you must choose the resonant or the natural frequencies as well as this damping coefficient. So if you see, these are the different parameter and V alpha, V beta for different PLL methodology. So these are the very important thing. And then we have, you can see that damping factor parameter K, as you vary, you can get different parameters. So these are the simulation result where you can see that different kind of PLL are implemented, and these are the simulation result. You can see here the PLL, that is voltage sag. You can see that this, you can see here all the PLL are compared here. And this is the experimental result of all these things, whatever we have done there. And this is our experimental result. And this is the summary, and you can see from here, you can understand what is the voltage sag and what is the settling time must be minimal. All these things you must take care while designing the PLL circuit. Okay, PLL for you. Then we used the proportional plus resonant controller, and resonant controller you are most of the time we have a proportional integral controller in the power electronics. In power electronics, we use this proportional and integral controller. Why we use this one? Because our references are DC. When you have a AC reference, so what you will use? You need to design like resonant controller, which will take care of the little variation in AC or the AC ripple or the tracking errors. Here you can pass and find out what is your the frequency, and then you design the parameters. So then if you see, this is a closed loop system and a current controller. Once you are designing the current controller, and then you design what are the parameters. So then we connected this complete unit with a DC-DC converter. Then we have a DC-AC converter, then a filter, and connected to the grid. Okay, the grid synchronization. And inverter control is carried out by using this one. This is nothing but the control parameter. The parameters are given in this one. You can see 184.7 watt actual system, and these are the parameters of that one. So then we simulated the system for maximum power transfer, this one, and then you can see that VDC is here, and IG, you can see as your insulation changes, the current IG also changes. Okay, you see the for low insulation, no current. Whereas we try to see this inverter voltage output, they are nearly constant, and that is how these conventional PLL are designed, and then they are implemented and also applied. Okay. So then we will discuss about the grid side converter of double fed induction generator. The most important thing, what do you mean by double fed induction generator? The double fed induction generator is that you can feed from both sides. For example, from starter and from the rotor. Then we call as a double feed. So you can feed from the starter as well as feed from the rotor side. So you have any induction generator, there is a rotor and there is a starter. So you can feed from both sides, and that is called double feed. And this one is there are two inverters which is connected. When this is used for the this induction generator, so you see the rotor is connected with two converter. One is AC to DC converter, another one to DC to AC converter. So this is connected from the line to the rotor. Okay. And through this utility, the step down transformer, it is connected to the double feed. So there are two converters. One is your grid side converter. Okay, it is connected to the grid. Another converter which is connected to the rotor. So now the objective of this control of the converter are voltage regulation of the DC bus, bidirectional power flow, it can flow any direction, operation at any desired power factor, low current harmonics. So this is how this we want to, it is our design. Now we have this is AC. You can see that is this is grid connected through this converter and supplying to a DC link. From DC link there is another converter which supplying to the rotor. Okay, this is the complete unit. Now I have only shown that charging up to this capacitor. Okay, this DC link capacitor. So we have 6 switches. Okay, and we have a control signal, and we measure this VDC, and accordingly we control this inverter. When you control this inverter, you see this inverter can be just represented as like a AC. One side is your AC equivalent, another side is your actual AC. And both of them, they are connected by an inductor, L. And this one, if you see here, this V, the input and output both have same frequency. That's why it is sometimes called the synchronous frequency regulation. And this forward, you can operate at any desired power factor. You can operate at unity power factor, you can operate at leading power factor, and you can operate at zero power factor. So the vector control are VAN, VBN, and VCN. You can just write down this and the equation for this, and then DC. If you convert from ABC to DQ parameter, you can get the equation here. You see, in this equation, you can observe in the D-axis, it depends on the Q-axis current, and in the Q-axis, there is a dependence on the D-axis current. Okay? That means the complete system is coupled together. Okay, they are coupled together. So what you will do first, as a design engineer, you want to discouple both the things. You want to dismantle the thing, and then you can easily design this one. For example, here you can see that in D and ISQ, okay, and here ISQ and ISD, okay, they both are coupled. So how to do that one? So these two equation can be the coupled equation can be taken out by in the gain block in the controller block. So now you see here, I have a voltage DC bus. I don't think that here any markers are. How to go to marker? Yes. So we have here VDC reference, because we want to keep the DC voltage constant. VDC reference and measure actual VDC from the DC, and both you compare here and pass through API controller. Okay. So this bus voltage controller is nothing but API controller. It will give us the ISQ, Q-axis current, and then you can feed this actual Q-axis current from the current sensor and pass through a PI controller. Then it comes to the feed forward term, then ABC to three-phase transformation. Okay, I told you. So you require to transform from ABC to DQ and ABC to alpha beta, alpha beta to DQ. Again, when you are designing this controller, then you need to again go from ABC to alpha beta to DQ. So like that, you can go in both. So this way, and by changing this ISD, so you can change the phase difference or phase difference. So if you see here, in this block, in the closed loop block diagram, there are many things. First thing is our plant transfer function, which is nothing but G divided by 1 plus STD. So this TD is the delay time. Okay, if you say here, the STD is your delay time, and you can see 1 by R divided by 1 plus ST is your inductor. Okay, inductor which was there in your input, and then we have in the feedback you see K2 divided by 1 plus ST2. Why we introduce this one? Generally, feedback path we have a unity gain. 1 you bring from output and connect to the input, it is 1. Okay, so that is called the unity gain everywhere. But here we put K2 by 1 plus ST2. Why? Because if you take actually a current, you can say the A to D converter. A to D converter, they required 1.67 microsecond to convert from one variable to other variable. So this ISQ is compared, and there is a delay circuit K2 divided by 1 plus ST2 is a delay. Then KC1 plus STC divided by STC, which is nothing but a PI controller, and this is the loop actually. So this is a PI controller, then the plant, then the inductor transfer function, then there is another the uh, the the feedback path gain, and then it comes to ST. So the closed loop control current control, you can see that in the closed loop there exists 1 plus ST2, there is a 0 in the system, and this 0 will create the oscillation in the network. So to cancel this 0, what we do in the feed forward path, you can see that 1 plus ST2, which we multiplied here, and this will stabilize the system, where it will cancel out 1 plus ST2 in the 0. So this is how we have a design. Then this complete current controller, I have taken as a small gain as a K, then complete design I have done, okay? And then the voltage control, you know, the current controller is very fast and the voltage controller is very slow. That's why the voltage, first we design the current controller, then we are designing the voltage controller. You can see that this is the voltage controller, where there is also a feedback because the voltage sensors are connected, and when you are converting from voltage, the A to D converter, when they are changing, there is association of there is association, there is a delay associated with it. So that is what it is shown here, and this is a PI controller, and then current, and then you have 1 by SC, then you got VTC. Similarly, the complete unit is the transfer function of this complete unit is found out, and you can see here this is the transfer function, and in design, voltage controller time constant is 10 times greater than the current loop time constant, and this is the our controller design. Okay, you can see there is a phase margin, and there is a the gain margin and phase margin, you can find it. Then we did the simulation and simulation study. We test the grid side converter. So what we did, we have one side, we feed from this 3-phase through the grid side converter. We charge this capacitor and connect it to the load resistance. So to understand the bidirectional power flow, the power can flow in bidirectional. So what we do, we use a auto transformer. We have a 3-phase bridge. Then we have a filter. Then we fed this through a resistance to charge this capacitor S1. And to dissipate in the resistance, that is by turning on S1 and S2. So you see that in this one, as soon as the DC link voltage will go, for example, VDC. So when the VDC is 800 volt and you get some across this load a little higher than the 800 volt, it will have a reverse flow. Okay, that to test that one, we actually simulated the system. You can see that the both and current, they are unity power factor. Power factor is 1, and they both are on the same phase. Okay, here. And then my DC link voltage is at 1. Okay, you can see that here. The DC link, in the DC link voltage is tracking to a reference value, which is 800 volt. Okay, so 800 volt is our reference value, where this is a tracking. Okay, you can see that there was initial voltage of 400 and it tracked to the 800. And if you see that, you see the IQ and ID, they are decoupled. You can see that one is showing 0, another one has some value. So similarly, IQ and ID, you see here, when you are changing the IQ, it doesn't affect an ID. If you are changing an ID, it doesn't affect an IQ. Like a DC motor, your armature winding and the field winding. So armature winding you do or armature current control you do, it will not affect on the field side. If you do the field side control, it will not affect on the armature control. And that is what the decoupled control methodology. So like that, if you see here, um, uh, it is time already 3:26. So I think we will try to finish quickly. Okay. So when the voltage, you can see that when the voltage, this link voltage is higher than this, so you can see that the current is leading to the voltage. Okay. So when there is a dip in the voltage, you can see that current is lagging the voltage, grid voltage. Okay. So that means you can operate at 3 even. So this complete unit is designed with 5 kilowatt. And if you see, this is our simulation, this experimental result. You can see this converter is operating and at unit power factor. And this one, you can see that it is operating at lagging power factor. And in this experiment, you can see that it is operating for the leading power factor. So at any designed power factor, you can design this system. Then the modeling of the rotor side. So how to do rotor side converter control? The rotor side converter control can be used by using decoupled modeling technique and advanced machine. And after that, we design model this complete the rotor side converter, and this is the DQ axis. Then DQ modeling and complete modeling is carried out, and then we have this PS and QS. You can see when lambda s is equal to 0, you take this starter reference frame. So we know that 3 reference frame. What do you mean by the reference frame? The reference frame theory is exactly like a trains. Like for example, in the Howrah station, you are sitting in a train and your friend also sitting in another train. Both these trains started at the same time, going at the same speed, and a 2 parallel rail. So what you will see, you see your friend sitting in the other train as a stationary, and your friend will see you, he will also see as a stationary. So both they will stationary because the relative speed is nearly 0. So similarly, whether you are in the starter reference frame, rotor reference frame, or arbiter reference frame, you try to make the things constant with respect to each other. Okay? That is what the complete reference frame theory. So this is the PS, you can see depend on IQS, and QS is depend on IDS. And this is our D-axis current response, rotor D-axis current. And then you can see that IRD. So you can see that it is not affected as we are changing the D-axis current. Okay. So now, whenever there is the rotor current, you can see that during this period, this rotor current injects the magnetizing current to the rotor. And these are the few references which we have taken. And there are few projects we developed. One is at Tennessee Technological University, where there was few challenges actually in this project. And this project was not long run actually, it was destroyed. And then second one, we have developed a big solar plant at Solar DC Microgrid at USA, and the minimal, there are a very beautiful design and with good infrastructure as well as the smart solar plant. Then design up to 200 kilometer per hour wind clearance you can. And optimal angle also we have designed. And it is a beautiful design and it is working till now. So this is, but the most important thing in the solar system is to design the specially to the grounding system, okay? And then the battery utilization, minimization of the battery utilization are the one of the important. Then we have a 1 megawatt direct feeding this PV system in IIT Patna. We have. Then there are also used in the many places like in the Chitragupta Nagar, in many places in Araria, where it is very small unit, 1.2 kilowatt each actually, that is developed. Then this is the another project at Vaishali District in Toipur. So this is a village here and the Toipur, and this is this complete setup is both solar ACDC, and plus you have a variable diesel generator, and it is completely smart actually, and apply for 50 houses. Then there was another project with Port Blair, where the Port Blair 1 megawatt solar plant we installed there. And this is the complete Port Blair design actually, layout, design, everything. And this is the cabling of the Port Blair, this one. And then this is installed there. So there are also few projects like in our IIT, but now we have IoT for smart grid, smart building, and they are currently it is people are using it actually, and this is a complete network actually we develop. Then we have also another imprint project where we do the planning and design of smart microgrid, and this is the smart microgrid. You can see here we have a horizontal wind turbine, vertical wind turbine. Then we have a solar tree controller and smart loads are connected. And if you see, there are a few project and micro hydro turbine also we carried out, and a few things also we did. And there are also hybrid solar controller design, and if you I can show one video of the DC microgrid, then we will stop here at this. So I'll show one simple video, and you can see this one. Okay, if you so is it time now?
So, how much time it will take, sir?
Only 2 minutes. This
Yeah,
video
sure,
one.
sir. Sure. Array, sir. Sure. 5 minutes, sir.
Only I want to show this video, DC
Okay. You can.
microgrid power, so that they can also see from the YouTube or everything we have uploaded there.
No, you can see. You can, sir. You can show me.
Sir, you can see now?
Yeah.
Okay.
Quite visible. Quite visible. voice is not coming in.
Okay.
Video voice is not coming.
Okay, sir. Thank you very much.
Okay.
And now, if anybody has any questions or comment. I have given my email address also. If anybody want to write any, they can also ask later also. If they don't have any question now.
So sir, now you stop that sharing the screen now. Please stop. Okay. Okay, sir. Sir, thank you very much for giving a nice lecture and motivating all of us on a very contemporary topic. I think if someone has question, they may ask, right? If you want to write, you can write. Sir has already given your email ID also. And sir is very generous to give the reply. Whenever you call, he will give the reply. So sir, thank you very much if people are not asking. And I hope in future, sir, you will accept my request and again enlighten us on this topic and many more topics, sir, right?
Thank you.
Thank you, sir. So, dear participants,
Thank you
now
very much.
second speaker is also ready